Um, Welcome everybody to the last session of this workshop. I'm pleased to introduce Nicholas Rubin from Google Research, who is going to talk to us about some interesting stuff on Sycamore. So Nicholas, whenever you're ready, you may go.
Thank you. Thank you for inviting me. It's wonderful to give a talk, and I'm happy to have the opportunity to tell everyone about the first experiments that we ran on the Sycamore processor after completing the supremacy experiment. So the simulation is of chemistry. It ended up being about twice as large as previous experiments and about 10 times as many 2-qubit gates. So I think it's actually a very nice step change in what we can actually simulate and a demonstration of what quantum computers can actually do, and shows off the device pretty well. So I'm going to have three kind of main components of this talk. I'll discuss NISQ to date and at least my perspective on it and how this experiment kind of fits in with that particular narrative and that roadmap. And then I'll talk about the majority of the time our experiment and kind of the motive. And I'll spend a lot of time talking about the motivation because I think there was a lot of response from the community and from the paper about why we're doing this particular experiment on our very large computer. And then I'll close with what we saw in the experiment, the system performance, and maybe the future of some error mitigation techniques. Okay, so this work is kind of the start of a broader research program that attempts to answer the question, are we on a path to quantum chemistry simulation advantage with quantum computers? So there's certainly been a lot of buzz around chemistry. It's a very important application of quantum computing. And I've listed some of the experiments, and this is down below here in chronological order. And this isn't all of them. This is kind of just like what I took from the literature as a first pass. But I do want to point out some kind of interesting things about this. One, that chemistry experiments have kind of turned into a litmus test of hardware, so a full system performance. You know, if you get one of these binding curves correctly, your system is performing particularly well. But I do want to point out that all these experiments are on fewer than 6 qubits, and they barely reach the accuracies that are required for deciphering chemistry with a computation. So this isn't a criticism of these particular experiments. It's more of an observation that it's actually extremely difficult to get these experiments to work. And it's likely that as we transition into the intermediate scale and large scale, either NISQ or fault-tolerant computations, that we're going to need new ideas coming into the field. So that's kind of where I start from in terms of this research program. And our perspective that we take from this is that we should work on scaling up important algorithmic primitives for NISQ and fault tolerance. So we should focus on simulating things if we're going to do a simulation demonstration, circuit primitives that we're going to need to run to achieve quantum simulation advantage. So there are some other things that can come along with this. We know that the NISQ era will be long and it will overlap with error correction. And so it would be nice if we learned and deciphered techniques that lowered threshold or improved the likelihood that an error correcting code we could run one of these codes earlier in time instead of maybe a decade. Another one is that, of course, coupled to that is that we want to learn which strategies are going to work best and the effect of noise and different types of error mitigation. And then ultimately, we want to answer how far are we from something that is actually classically intractable. So the chemistry experiment that we focus on is the performance limits of the basis rotation primitive and how we can improve that performance with various forms of error mitigation. And so we study this in the context of VQE, variational error mitigation, because when you couple this basis rotation with energy minimization, you recover a very well-known electronic structure method, Hartree-Fock. And Hartree-Fock is kind of the canonical starting point for many of the correlated calculations that you need to actually simulate some interesting chemistry like a catalysis system. So the basis rotation is actually a very important simulation primitive when you're moving to the full interacting model. So the basis rotation that I'm actually talking about is a coordinate transform on the one particle Hilbert space. So in chemistry, this corresponds to taking linear combinations of an orbital basis set to form a new basis set. So what I have depicted here, those kind of blobs are depictions of orbitals, and I promised you this forms an orthogonal set. And if you were to kind of integrate one against the other, you'd see that they're orthogonal. And linear combinations are these C coefficients where we're taking sums of them and forming these new basis functions phi. So when you actually represent this particular coordinate transform in second quantization, what you get is a unitary that generates dynamics that's quadratic in many body order. And so, like I said, if you couple this with energy minimization, namely change those kappa parameters, you get back the Hartree-Fock procedure, though in a slightly non-standard form. So those of you who are familiar with this will know that the iteration complexity of Hartree-Fock is cubic. Why would we do it? It's classically tractable. Well, the circuit, like I said, the circuit comes up everywhere in terms of our best algorithms for Trotter compilation and, for example, unitary coupled cluster. And I'll talk about those and give specific examples in the next couple of slides. But we also have an optimal compilation for this. And this actually comes from a Gibbons rotation decomposition of this particular unitary. But what it lets us do is focus on things that are closer to the hardware. Namely, if we have bias in our gates, how does that affect the output? So having a clean compilation of this particular unitary actually helps there. And ultimately, since we're simulating a fermionic Gaussian state, we have access to things like the fidelity that you normally wouldn't be able to get for a generic state without exponential measurement overhead. So the other thing to point out, I think that is important to say about fermionic mean field states is that they are entangled from the qubit perspective. And so from the perspective of your device, you are still preparing a very entangled state, which is an important benchmark. Okay, so after we put this paper out, to my surprise, it was kind of discussed on Twitter of all places. And this is probably a little too small to read, but I do think this person is asking good questions about the paper and why we actually did this simulation. For example, the first couple of questions here are exactly, well, Hartree-Fock is efficient to simulate. Why do you need to do this on a quantum computer? And I'll explain that in the next couple of slides. And then the others are kind of the natural questions that you have about other variational strategies. What is the measurement complexity? How does this actually move us towards improved measurement schemes? And what are the optimization strategies and things like that? So I'll talk about all of those. But I think it's always good when science kind of gets out into the social media in some sense. Okay, so what is up with my obsession with basis rotations? Like I said, they come up in some of the best known simulation algorithms that we have. And the next 3 slides are actually going to explain 3 areas where this actually occurs. So let's say that you're given a interaction operator that has this form V. And what you like to do is generate dynamics on a quantum computer using this operator V. So I've written it in a very suggestive form here. Chemists are probably very familiar with this form. Physicists usually order it with respect to normal ordering of a vacuum, where all the ladder operators are on the left. But what you can do, and I'll take a short interlude to explain this and how it relates to the basis rotation circuits, is what you can do is you can factorize this tensor, this V tensor, into a sum of squares form. And so that's the first line in this equality. And what you can do second is then factorize that one body operator that you get back into a set of charge-charge interactions with basis rotations on the left and right. And so this square here in the sum of squares representation just goes into the double sum over here. So why have I explained this to you? Well, if you try to implement dynamics from this particular decomposition, what you get is a sequence of basis rotations and then followed by charge-charge type evolution. And you just keep doing this for all L of these factors here. So like I said, this is our best known compilation strategy for Trotter steps of generic Hamiltonian with 2-body interactions with no other structure other than maybe the rank of the operator. And you can also do this for a unitary coupled cluster. And so it's a pretty attractive thing to do, at least when you're not thinking about.
Nick, yes. Can I interrupt you 1 second? Several
Yes,
people are finding problems hearing you because there is a bit of noise. can you try removing your headphones? Maybe that will improve the...
Yeah, let me try maybe a different set that will work a little bit better.
Okay, how's this?
It's the same.
It's the same? Okay, let me see. Okay, well, I don't know if it's going to get better than that. I can hold the mic closer to my mouth.
There's a little bit of echo. I don't know if, well, some people are saying that it's better, but I don't know if, what about doing it without headphones?
How's this?
No, it's the same. Okay, the problem is not the headphones.
Sorry, I didn't catch that.
It seems that the problem is not the headphones.
Okay, maybe it's the room that I'm in. I don't know if I can change that.
Well, I guess we'll have to try to continue.
Maybe I'll try to speak a little slower and so it's a little clearer if the audio is going in and out. Sound good?
Well, it's better. There is echo, but it sounds better.
Okay. So where was I? Right. So the simulation of a two-body interacting system, or two-body interaction here, the best known compilation is with this double low-rank factorization technique, which inherently the basis rotation comes up in. And so you can use this as a NISQ primitive if you like. You can parameterize the basis rotation and the charge-charge interaction. And you can use that as a way to actually do a VQE simulation if you'd like. Another place where this comes up is actually addressing the measurement problem that the Twitter user was mentioning. And let's say I have a Hamiltonian that's the normal form for ladder operator form of electronic structure. What I can do is do a similar double factorization into a form that looks like this, where I've just diagonalized every kind of component into a sum of squares term. And now what I can do is just measure my Hamiltonian in every single one of these UL bases. And then all my measurements are too local and involve just Z local Z measurements. So I can measure everything in Z basis. So what you get is a sequence of measurement circuits that look like on the left, right? So for the first kappa basis rotation circuit here goes into U1, and then the last one goes into UL, and you just iterate through all L of these. And we know from chemistry that L is going to be around n to the third because of the structure of the Coulomb operator. So if you were to do some numerics on scaling of this particular technique, you see that, and I know this is a little hard to see, so I'll just kind of explain at high level, is that if you count the total circuit repetitions to measure your Hamiltonian to a particular accuracy, given the variance of the state, you see that this strategy is one of the best that we know of. And so you're going to need to simulate these basis rotation circuits to perform the best or the lowest scaling measurements for near-term quantum computation.
Nicholas, can I interrupt you again for a second?
Sure.
Some people are finding it difficult again to hear you. Can you mute something in your laptop?
There's really nothing running on my laptop. There's only one other window open.
No, I don't think
very quiet here.
Okay, well, we'll have to do it like this. Yeah, please continue. Thanks a lot.
Yeah, sorry about that. I really don't know. I haven't had this particular problem before. Okay, so The last example is something where the basis rotation circuit doesn't come up directly, but a form of the circuit is the basis rotation circuit comes up as kind of a sub-piece of this circuit. So let's say, for example, you would like to implement a sequence of the gates that I have here on the right. So this 4x4 unitary, this 2-qubit unitary. And what I've written it in a pretty suggestive way. This is called an fsim gate followed by a swap operation. And what it is a fermionic simulation gate, namely it conserves charge interaction. It conserves particle number. And what I'll tell you is that the basis rotation is actually just the odd subspace component of this. And so you can see right away that if you have a basis rotation circuit that implements the core the odd subspace of this gate pretty well, then it's not so far away to imagine implementing the even subspace to get the full interaction gate. And so I think this is actually kind of an interesting extension of this experiment, because if you actually count the Schmidt coefficients of this gate, you'll see that it's 4. And this means that it's difficult to simulate, at least in a Schrödinger-Feynman type simulation. And so there are other reasons why this is an attractive kind of beyond classical primitive for chemistry simulation. On the left, I've indicated what this might look like if you were to compile it to a linear architecture, namely even and odd pairs of qubits are getting this interaction with this fsim gate. And you can parameterize all of those gates with T and V that I've listed here in a NISQ type setting. Another example is if you want to learn Schroeder steps or the Hubbard model, you'll get interaction terms that look exactly, or you'll get terms that look exactly like this. For example, you might partition your Hubbard model into dynamics of the one-body hopping for the odd subspace and then the even subspace, and then maybe interleave the charge-charge interaction. And you can compile that charge-charge interaction into the odd hopping, for example. Okay, so that's why this circuit is, I think, very important to the basis rotation primitive, and that's why I keep calling it that. So let's talk about what this actually looks like on the device. So after we compile it to the Sycamore chip. So Sycamore has gates that look like this one that I depicted here on the right. It's an fsim-like gate, and we have control over all of the parameters the variables that I've listed in the gate. So the I swap angle, theta, and then the local Z fields that we have here, and then of course the charge-charge interaction, the 1-1 evolution. You can pick out a line on your grid. So I picked out a subgrid of Sycamore and I've just drawn a line on it. And then you can compile the unitary for the basis rotation into that line. So the compilation that is required for this unitary, as I said before, there's no Schroeder error. All you need is linear connectivity. And the way that this works is it's actually QR decomposition of the exponentiated kappa matrix. And this is due to the homomorphism between a one-body Lie algebra and the full U matrix on the full space. So what I have depicted on the left is a 12-qubit, or a 12-hydrogen molecule in some initial basis set that I start with. In this case, it's the core Hamiltonian basis, so I just diagonalize the kinetic energy and the electron nuclear attraction component, and that's just a linear size Hamiltonian. And you get some orbitals that might look like this. And the goal is now to minimize the energy with respect to those kappa parameters, and each of those thetas are what you get out of this QR decomposition. And so the thetas don't directly relate to, or the kappa parameters don't directly relate to the thetas. You have to do this pre-processing step. So there are actually lots of ways to compile each one of these thetas into a given rotation. But what we find is the best is this particular strategy that I've denoted here. And the way to think about this is to think of the square root I swap as a local fermionic Fourier transform. So every given rotation gate, what we're doing is rotating locally into the diagonal basis for the two fermions. So doing a local Fourier transform, evolving in the eigenbasis for theta, and then going back, doing I swap theta dagger. And to get I swap theta dagger, we just put 2 whole z pi gates. So the interesting thing about this is that there's no microwave control, and so that lowers the number of kind of lines that are going into our circuit, and we don't get the error channel that one would get from microwave control. It's just voltage offsets with the z gates. So this is nice. It means that we can do these circuits actually with much higher fidelity and then roll the control of the theta, the z gates into the I swap parameter. And of course, after measurement, and I'll explain how we do the measurement for the 1 RDM at the end, we can apply things like post-selection because this entire circuit preserves particle number. Okay, so that's the circuit, and that's the ansatz that we're going to be using. The next component of NISQ's experiment is measurement. So generically, to measure the energy of a chemical system or electronic structure, you need the expectation values of these quadratic and quartic many-body terms. And so a matrix of these expectation values are canonically known as the reduced density matrices, and what they are fermionic marginals. So they're the fermionic version of qubit marginals. And there's lots of structure that comes from these, and normally you have to measure all n to the 4 of these correlators. But for our particular experiment, where we're focusing on fermionic Gaussian states, we actually have an explicit reconstruction from the 1 RDM, so these guys, these quadratic terms, up to the quartic terms, and that's this expression here. And so this is very rare to have this exact reconstruction, but you can kind of understand this by remembering that for Gaussian probability distributions, all higher order moments are described by the second moment, and so that's what we're leveraging here. We can just describe all the higher order moments from products and combinations of the second order moment. One thing that comes along with measuring just these 1 RDM terms, so just these guys, is that we are greatly reducing the number of measurements, but also that there's a very well-known geometry of these particular quantum marginals. And so by geometry, I mostly mean a set of equations that they must obey. So for example, we know that this particular marginal, this matrix of expectation values, has a fixed trace, and that's equal to the number of electrons. We know it has to be an idempotent operator or an idempotent matrix for fermionic Gaussian states, and we know it must be positive semi-definite. So, which comes from the idempotency constraint. So what we can do is use this geometry and use this information to actually do error mitigation. And let's say we measure a state at 1 RDM that gives us something else. This is a set of 1 RDMs that obey the geometry that I'm just talking about. What we can do is project it back to the boundary, thus purifying our state. So the way that we actually do this is through something called McQueenie purification. And what McQueenie purification is actually a gradient condition on the loss function for idempotency. So namely, if you were to say, give me my density matrix as a function, write down a loss function where I have rho squared minus rho, and then I take the derivative of that and solve for what the update would be, you get exactly what this particular update is here. The way we implement this in the experiment, instead of, or as a post-processing step, instead of just diagonalizing 1 RDM and fixing the eigenvalues, because you can derive sampling bounds for the stability of this particular procedure. And so that gives us actually a bound on how many samples that we need to take. So you might think immediately, well, this is kind of hard to generalize. You don't always get this very nice structure because you're working with Gaussian states. But there is other non-trivial structure that you can use as error mitigation techniques. And we started that discussion in this particular paper, but I think there's actually a lot more that you can look into here. And so that's kind of an error mitigation direction that comes out of this work. Okay, so I want to take a little bit of time to explain how we do the measurements, because I think that component of it is also generalizable to the full interaction model. So the goal, of course, is to measure the load of 1 RDM. So all expectation values here that I have listed for all indices ij. And I'm going to explain how to do this with first an example. So let's say I have my circuit, and this is a 6-qubit version of the experiment. And I measure all nearest neighbor pairs to the x and y basis. So I measure all x and then all qubits y. And you can see with a kind of short calculation that what you get is the sum of all one off-diagonal 1 RDM elements. So it's the highlight. I highlighted those elements in red on the matrix on the right. Now, if I was to perform 2 extra swaps of these fermionic modes at the end of my circuit, I would actually get a different set of 1 RDM terms that I would be measuring, and I've highlighted those in orange. And the F swap is actually just another quadratic operator here, so it's just swapping the labels of 2 fermionic modes. And you can kind of see right away that if I keep doing these swaps, I can eventually cover the entire 1 RDM. Now, of course, I've added swaps at the end, and so I'm making my circuit longer. But what we can do is actually roll these swaps back into the structure of the given rotation network. And that's using this particular property of fermionic Gaussian states. Namely, if we have 2 Gaussian states, UA and UB, their product is just the product of the smaller UA and UB representation. So this is what I mean by the homomorphism between these representations. So just very quickly, we can actually measure, we can post-select on particle number for everything by then rotating, doing another fermionic basis rotation into one that diagonalizes the XX plus YY operation, and then just measure local Z 1 qubit expectation values. So you can put all of this together and then measure the entire 1 RDM, and that's the strategy that we use. What's changing is the structure of these coefficients data that you get from the QR decomposition. It's actually the same as reordering all of your fermionic modes and shifting around all of the columns of your basis rotation that you're trying to do. And so the effect is the same. You can put the permutation at the beginning or at the end. Okay, so for the last, I think, 10 minutes here, I'd like to talk about how well does the machine do and what we get out of the experiment. So I'm sure many of you know Sycamore by now. It's a superconducting qubit platform. It has 54 transmons in a planar array. They're tunably coupled. They give you a gate like the FSIM gate. It looks like that. Here's the CEO of Google standing next to the computer for scale. So there's lots of wires that go into it. And you'll get performance out of Sycamore that looks something like this. So for single qubit gates, we have about 0.15 poly error. Our 2 qubit error gates per cycle are about half a percent in terms of poly error. And then the readout is actually around 97%. And so readout is still kind of the place that we can improve quite a bit. But there are ways to actually post-process a readout if all of the readout error is just from T1. You can just invert that channel and then mitigate this. And isolation is pretty good because we have these tunable couplers. We can isolate the qubits well when doing single qubit operations like 1 qubit gates and readout. So most of the data that is collected for the experiment was done through the cloud interface that the team will be releasing hopefully soon. And so some of you might already have access. And that's accessing our chip through Google Cloud Platform and using Circ to send circuits to the device. And so in this case, we're using Circ and OpenFermion to do the chemistry piece. So just as a recap, this is a smaller example. This is a 6-qubit example, and this is what the circuit looks like. We start in a computational basis state indicating the particle filling. In this case, it's half filling. And then we implement our QR decomposition generated circuit that produces a new basis set that hopefully minimizes the energy. So we can start looking at kind of the canonical example in electronic structure, which is hydrogen chain dilation. And what I'm going to do is simulate a series, 6 qubits, 8 qubits, 10 qubits, and 12 qubits, or 6 hydrogens, 8 hydrogens, 10 hydrogens, 12 hydrogens. And the reason that the number of qubits are matching the number of hydrogens is that I'm only simulating one spin sector here. So in the restricted Hartree-Fock formalism, the spin up sector is equivalent to the spin down sector in terms of their basis rotation. If you want to do UHF, you could actually just simulate both of them or both sectors separately and then minimize the energy with respect to that. Or if you want to do GHF, it would just be a circuit that's twice as large. So for the 6-qubit case, if you compile a circuit like I have depicted above, you get about 18 squared I swaps and 27 RC gates. If you do go up to 8, you have 32. And then you can do 10 and 12 and go all the way up to 72 squared I swaps and 108 RZ gates. And so what I have depicted in each of the figures is the data that we're getting back with various forms of error mitigation. And I'll talk about each one in the next slides. Yellow is the raw data, and then green, blue, and red are the error mitigated data. And so for 6 and 8, we actually are getting below chemical accuracy for this particular system. And for 10 and 12, we're just about reaching it, but not quite there. And so this is actually why we don't go beyond 12 qubits, is because the goal is to actually simulate something close to chemical accuracy. So this is a diagram of our optimization for BQE. So one of the benefits of simulating Gaussian states is that you have access to the gradients for the entire circuit. We derive it in the paper, but it's a fairly well-known result for closely algebras. And I've plotted the variational trace, or the trace of the optimizer, as a function of iterations for 3 bond distances, just to show that we are consistently lowering the energy with variational optimization. It's not just hopping around, so we do have some degree of stability. And we do get variational relaxation over about 2 decades, which I think is enough to say that it's actually performing error mitigation consistently. So what are the fidelities of the system, and what do we get by layering on error mitigation? So here is kind of another zoom in of the 6-qubit case, but I'm also providing data for the 8 through 12 case. So the first yellow line here is just what we get by running the circuit, no error mitigation. This is exactly what we just pull off the chip. And what we can do is say, look at the elements of the water RDM and derive a fidelity witness. And a fidelity witness is something that strictly lower bounds the true fidelity for all states. And so we know that when the fidelity is very low, the fidelity witness will be kind of trivially loose and not meaningful. And when the fidelity is very high, it'll be tight and actually be giving a very nice description of what the fidelity of our circuit actually is. So right away, we see that we're going kind of from 60% fidelity all the way down to about 1%. And this estimate column here is what we would get by estimating the fidelity just from the supremacy numbers. And so what this tells me at least is that kind of all the components errors are adding in a way that is known and not kind of nefarious in some way. So we can start layering on various error mitigation. One thing that we know from chemistry is that particle loss is a huge error channel. You can't lose electrons in your system, so accounting for that with post-selection actually is a huge boost. And part of the reason why it's a huge boost going from about 1% up to 60% fidelity for the largest system, H12, is that the fidelity witness actually depends or is calculated by kind of reverse transforming your measured 1 RDM into a diagonal basis and then counting up the occupation in that basis. And so if you're losing particle number, counting those up ends up being a pretty large loss. And so we can see that even with something simple like accounting for T1 with post-selection, we get quite a bit of boost in fidelity. And we are doing this on the entire 1 RDM, not just the diagonal elements. What we can do is then apply the next layer of error mitigation, which ends up being this purification. And through a short calculation, you can show that this actually is mitigating T2 errors. And so with this, we're getting up to quite high fidelities, almost 99% fidelity for the 6 and 8 qubit cases. And then, of course, if we allow variational relaxation despite calibration for large circuits, we do see that we can error mitigate for parameters. One thing to call out is that even at H12, we're at 99% fidelity for the Gaussian circuit, and we are still above chemical accuracy for all the points. And I'm just plotting that here to show you that nothing changes drastically as we scale up the system size. So what that means probably is that one, we'll need new ideas, and also that we might just need to wait for error correction to come along if we want to do this type of chemistry at this scale. Okay, and the last example I want to close with is kind of putting all of that together, so using all the error mitigation techniques with variational relaxation on the Gaussian circuit to look at a chemical mechanism. So this is the first time that someone's done this on the device. Let's say in chemistry, what you'd really like to do is know how a particular transformation happens. And if you have that knowledge, you can just determine what chemistry is happening and then maybe even design around that. And so the first step is simulating the reaction pathway. And this is kind of the simplest reaction pathway for a very simple system. So what I have here is diazene. That's 2 nitrogens and 2 hydrogens, kind of in the structure of hydrogen peroxide, if you're familiar with that molecule. And the mechanism that I'm studying is the isomerization from the cis configuration to the trans configuration. So there's 2 possible ways that this could happen. We could do an in-plane rotation of this hydrogen. It flips up to the same side as the other hydrogen, all in the same plane, and that's this red curve. Or you could rotate the entire dihedral bond, and this hydrogen will go from one side to the other. Now, what is known about this is that this is, of course, well known. This reaction is used as a benchmark in quantum chemistry all the time. And Hartree-Fock is known to reverse the transition state order here. And so we wouldn't be able, this is not a good model chemistry for this particular system. But the point of this is not to test the chemistry model of a quantum computer, is to test the accuracy that we can get with error mitigation. Like I said at the beginning, the performance limits of the basis rotation primitive. And so it's a nice target to look at. And so if we run this on Sycamore and with all of our error mitigation and optimization, we get these results. And so it ends up looking pretty good. We certainly deciphered the correct transition state. That's a gap of about 40 millihartries, and so it's sufficient. This data is sufficient to say that at least from this, using this chemical model, it would be going through transition state 1. Of course, we know from higher order calculations and post-Hartree-Fock calculations that that's actually not correct. And so it's kind of sees the difficulty of actually doing chemistry and simulating chemistry overall. But what this says is that Sycamore is performing as expected, and we can get accurate systems from quantum devices today. So let me just conclude as I come up on 40 minutes here what we did. So we realized the largest chemistry experiment by far, so up to 12 qubits, but scaling past 20 qubits with the current strategies seems pretty difficult. We probably can push it to about 20, but we're going to need a new change in how we do simulations going into the future. It might involve just getting error correction. The onset is 3 fermion evolution. It corresponds to Hartree-Fock, but this basis rotation primitive comes up kind of everywhere when you're thinking about the best measurement strategies for NISQ and other compilations. We have ways of addressing the dominant error channels in our circuit, so T1 errors, systematic errors really with variational feedback, and even with our best calibrations, we still see that variational feedback is effective at lowering the error by about an order of magnitude. And I think this is a nice step towards intermediate scale and is a nice thing to be testing on different systems. So one thing I didn't talk about here is that you could actually run this particular benchmark in other modes. You don't have to use VQE, you could run it in a phase estimation mode. And that would be like kind of a next step in terms of quantum algorithms and demonstrating system performance with controlled evolution. And so I think this is actually, the Gaussian circuits are actually a very nice playground for benchmarking and kind of showing the performance of particular devices. And with that, I'd like to conclude. Thank you. This is actually a huge team effort. Of course, I had nothing to do with building Sycamore. That's kind of all the hardware team and the electronics team. I wanted to point out Vadim and Charles Neal, who were very important in getting the calibrations working for this and running the actual circuits on the chip with me to get them to work. It's always good to have an experimentalist next to you to tell you where you're going wrong. And of course, my members of the team that I'm on, Ryan and Jared, for kind of working on the theory with me and getting this experiment run. With that, thank you so much, and I'm happy to take questions.
Thanks a lot, Nicholas. For a very nice talk. I'm going to go to the Slack channel, see if there are any questions. I have a couple of questions from Nathan Fitzpatrick. So Nathan asks in his first question, can Givens rotations be used in a full configuration interaction setting? For example, if you had a basis of Slater determinants rather than spin orbitals?
Could you say that again, the full interaction, the first part of the question?
I'll repeat the question, the full question. So can Givens rotations be used in a full configuration interaction setting? Like, for example, if you had a basis of Slater determinants rather than spin orbitals?
Yes. In some sense, that's what we're doing. Of course, when we implement the unitary, we're starting from in this case, a computational basis state, which is representing a Slater determinant. And so all computational basis determinants. And if you were to layer this particular circuit into, let's say you started with an MCSCF state or a CI double state, for example, this basis rotation would then be doing a full CI basis rotation. And that is not necessarily efficient to simulate.
Mm-hmm. Why wouldn't it be efficient?
If you start with a many-body state, if you apply a quadratic operation, you still need to evolve in everything, right? It's only efficient when you start from another efficiently described state, like one of these computational basis states.
I see, I see. Okay, there is a second question from Nathan. So, for your gradient function, you say it holds for closed Lie algebras. Does that mean it will also hold for the spin orbital space, which is described by the Lie algebra of U2n?
So the gradient you can always write down either in, so U to the 2 to the n sounds like the full developing algebra for the full space. It will certainly hold for that, but it requires an exponential measurements to get the gradient there. You need the full density matrix. In this case, since our algebra is just generated by quadratic operators, getting the gradient actually just requires the one RDM, and that's because the one-body operators form a closed algebra. That's linear, or it's quadratic in size, but the adjoint matrix is just linear in size.
Mm-hmm. Okay, thanks. See if there are any other questions. I'm going to ask a question myself about the purification method you used for your density matrix. Would that work also for for other things rather than Hartree-Fock, like for example UCC, correlated calculations?
Yeah, so the purification step will not work when you're not simulating a fermionic Gaussian state. Let me be very, very clear. You cannot port that over to a generic NISQ calculation on chemistry. That comes from the structure, the eigenpotency constraint of the 1RDM. Of course, you could start to design other procedures that use the geometry in other ways, like what we described in that paper using N representability, projection, and things like that. And so they're kind of techniques of similar flavor, but applying McWeeny purification as described in the paper, and as I described in the talk, does not generalize necessarily. It more points in the direction that using RDM and geometry constraints is a kind of an interesting way to go for error mitigation on NISQ.
Okay, thanks. See someone typing something. Let's wait. So Nathan again says, would it be possible to explain the answer that you gave in the video in more detail about the inefficiency of the Gibbons rotations in the previous question in the FCI setting? He was confused by why it wouldn't be efficient.
Well, it just is that if you have an arbitrary state, like any wave function, and you want to apply the unitary that corresponds to the Gibbons rotation, the circuit is the same. Like there's no change to the circuit. But if you're to simulate that classically, you still have to propagate the entire state. And what I contrast this to is Hartree-Fock, like we're doing in this particular experiment, or if you're doing, for example, a MCS experiment where you have knowledge of the 2RDM. There, you just have to evolve your RDMs and see how your energy is minimized. If it's still, I guess I'm not exactly clear what they mean by efficient here. The circuit itself doesn't change. If I want to do a basis rotation in the full CI space, then I'm doing the same circuit.
Okay, thanks. Any other questions? Maybe I have a kind of a question in terms of how important is it to have this kind of interaction between theoreticians and experimentalists in doing these experiments?
I actually think it's very important. So I described the compilation of this circuit into kind of squared I-swap gates and how those are the fermionic Fourier transform on kind of two fermionic modes that are next to each other. At the beginning of this experiment, actually, we just had the Sycamore gate. If you remember from supremacy, that was an I-swap with a C phase of like pi/6, right? And so when we started doing these experiments, one thing that we were able to ask from the experimentalists is like, well, if I want to compile this circuit with Sycamores, and we show them how to do that, it's about 4 Sycamore gates per Gibbons rotation. And that would have, I mean, that's a huge overhead in terms of just implementing one of these 2-qubit gates. Really, the theoretical lower limit is just 3 Sycamores. And so if we work a little harder, we have a little bit extra gates, but it still isn't exactly clear that that's the best way to go. And so we were able to ask the experimentalists for a new gate. And they gave it to us, this I-swap gate. And we had a good reason to do it. It's that this Gibbons rotation is exactly implemented with this thing without microwave gates. And so it was kind of imperative for getting the experiment off the ground, being able to ask for particular gates.
Wow, very interesting. Nice.
I think actually to follow that up, the long-term view is, of course, that we have full parameter control over all of the pulses that are going into the FSIM gate. So there's actually no compilation overhead. It's just we're implementing the FSIM gate as a 2-qubit unitary that we're controlling. But it's much easier to calibrate a fixed angle for all of the 2-qubit interactions, which makes my experimentalist lives easier. And so then it's on us to actually do the compilation into something that they give us. So.
Oh, very interesting. Well, I have the impression that there are no more questions for the moment. Well, I guess that's it for today. I guess we can finish now this talk, which has been really, really interesting and lots of things to digest here. Thanks a lot for giving us this talk.
Thanks for having me.